Hello, this is Daniel Bingaman. I've been working on a project to make a All-American 5 style radio from scratch. Yeah, except we made a few changes. We call it the AS4. It stands for American Safe 4. The 4 being 4 tubes instead of 5. I chose to use solid-state rectifier instead of a tube. And the other difference is being the word safe added to it is because it has two transformers. It has a transformer for the filaments and it has a transformer for the B plus voltage. And stay tuned, I have more to show. Okay, so here is the schematic for the AS4 revision D1. Yeah, a lot of revisions. We had to make a lot of changes to make this thing work. I started out with a schematic that was on the internet where it had a really nifty way of, but I went through it one by one and I was able to eventually get the schematic straightened out. I then modified the circuit, which was originally for All-American 5, to this transformerized All-American 4. We have our power coming in down here at the bottom. It's a 3-prong American style hot and neutral and a ground. And then we have a fuse and a switch. Yes, I do put the fuse in front of the switch. I know some people argue over the direction of that, but anyway. And these two transformers, tubesandmore.com, antique electronics supply. They still sell those, and those are modern transformers. They're not new old stock. The first one is just an isolation transformer for the B+, and the second one is a filament transformer. Notice it has a center tap. Center tap is grounded, and that helps to reduce a buzz in the system. And it's a common practice in a lot of good quality audio equipment and so forth. The B plus transformer goes then to a full wave bridge. And the full wave bridge, since it goes in and then it goes through that and then through some filter capacitors, you wind up with about 170 to 180 volts AC, which is a really nice voltage to work with on a tube radio. The F2 fuse, that really should have been down here below, but it's already passed. It's happened. It's on the board. Next revision I can get rid of it or move it. And I know it's a little redundant to have a fuse on the primary and secondary, but I'm just being extra safe and I don't want to burn those transformers up. The antenna and ground terminals on the back of the radio set. You have the antenna going into a 10 microfarad capacitor, which isolates it electrically from the rest of the system, but allows the RF to go through and into the tuning, into the LC circuit. Now, so we have our our band for the radio signals coming in, and we have a 249 microhenry coil, which is on a sewing bobbin instead of being a big loop on the back of the radio like your typical American 5s, or having a coil on a ferrite loop stick. Well, I didn't do either one of those. I had these sewing bobbins on hand, and they were easier to chuck in my drill with a nylon screw and put that on the board, and that's what I did. In hindsight, probably would have been better off doing it the other way with the bigger antennas, because it would have improved the sensitivity of the radio. Uh, and I had to require an outdoor antenna. This set has to have an outdoor antenna in order for this to work. Otherwise, you need to make the other type of antenna. The variable capacitors, where the band and the band spread and the local oscillator, the rotors are tied together. And I found out that is actually a commonality on variable capacitors. Who would have thought that the rotors are the part that's tied together? But they are. It's reality. And so all of that had to be tied together. And so I had modified this circuit to accommodate that I originally had. In this coil, the other leg of the coil, instead of tying into all that, it is isolated and joins the AGC circuit, so that the AGC voltage can go in there and turn down the power when overly powerful radio station gets into the system, and that works. The IF transformers. I had one heck of a time finding good IF transformers. Another thing, they don't tell you anything about impedances. You see, the input and the output of an IF transformer has impedances. It's windings for high voltage, windings for low voltage. You have to know that. But guess what? They don't put that in any of the documentation. That is anyway, that made it very difficult finding the right parts. I wound up going through 4 different sets of IF transformers before I finally found something that works, and a number of those were not because they didn't work, not because of the impedance, but because some of them had silver mica disease. The nice big fat IF transformers, the old style ones, are much more reliable, and that's what I used. And they're also more related to the period of the tubes, which actually kind of helps guarantee the impedance in a way. So they're in there, and they're working. Sometimes the capacitors go bad on the little mini capacitors on those. They get holes poked in them, or somebody over tightened. Somebody did something to them anyway. I don't know what, but I finally found some that worked. And then we go into our 12SQ7. So this tube is a triode with 2 vacuum tube diodes on pins 4 and 5. They work in relation to pin 3 on the cathode there. And you can use both of them, or you can use just one. You don't have to worry about using the other. You can tie the other one either way. You can tie it to 4. You could tie 5 to 3, or you could tie it to 4. It doesn't really matter. It doesn't matter which one you use. Anyhow, in hindsight, you get a little more performance out of using a solid state diode, as there's a lot more loss in a vacuum tube than there is in a solid state. Even though diodes have voltage drop as well, it's bigger in tubes. The radio phono switch. It works, but when you get a really powerful station, it does tend to bleed over, even though I use shielding on it. But at that point, I really didn't care. It's just in fact, I had thought about building the radio without the switch, and anyhow, so I really didn't bother with it too much. The volume control, you want to make sure that those are shielded. Uh, and but going on, the biggest problem was in the output stage. You see that 12L6. Now in your All American 5s, it's a 50L6. There's no difference to that. The 12 volts is the filament voltage for this. Whereas 50L6, it's 50 volts. And the problem was C3. The capacitor you see across the output transformer originally was across pins 3 and 8. And it was made some really crazy oscillations that even a lot of seasoned electronics people had a hard time trying to figure out what that was. I shared scope patterns with them and other things, and we finally, somebody made a good suggestion on a EEV blog, and putting it across the output transformer. I moved it and the problem went away. Yeah, so anyway, it was quite a project. Finding the values for the output transformer, the right ganged variable capacitor for the circuit, the right local oscillator. All these are various things that I'm going to discuss, and I'll get when I get to those things later on in this. For now, let's go look at the printed circuit board. So here is the printed circuit board layout. This is an old printed circuit board software called Super PCB by Mental Automation. It is an old program, over 20 years old. But I know it like the back of my hands. That's why I use it. So when I started this circuit board diagram, when I started this, there was, I had some ideas that, well, lack of knowing how certain things are done. I had this thing where I tried to mimic the crosswire, the spin, rotating the wiring of the heater, doing this to cancel their magnetic fields. Well, I had somebody who had a lot of experience with this stuff told me, you don't need to do that. He says it's because they are on a circuit board, you just put one on the bottom layer and one on the top layer right above it, and that will do enough to take care of the magnetic field. I even had some little crazy shielding ideas like this, and the one on the opposite side right here, and I really didn't need those. But I'll tell you what, the circuit does not make a lot of noise, so it does what it's supposed to do. So coming in here, we got our place for from our transformers, our power for the high voltage is here, and the heater power goes in here, and this then connects to the diode full wave bridge, and then through the fuse, and it's got the capacitors here to filter the power, and B plus feeds the 12L6, and then right after that we got our little 1.2K actually it was not little, it's a 5 watt resistor. I went oversized just to be safe, and then over here's our capacitor for the B plus, and so the primary and secondary B plus rails run straight across here, and the ground rail runs across the bottom here, and so I try to keep all my power organized in that manner. Um, and then we got our 12S A7 tube socket. My first version of this, I actually used relay sockets um, as an experimental one and had standoffs, and I got to where I really didn't like that, so I decided to make a circuit board. And you gotta thank JLC PCB for the fact that you can get such affordable prices on printed circuit boards to do that. Well, so here's the antenna coming in for the system, and there's the place for the capacitor to bring it in, and it can go to alternately. You can have an antenna coil on this pickup here. Well, anyhow, um, local oscillator coils are over here in the corner, and that all worked out really well. Tried a lot of different ideas with the hooking up the IF, and in hindsight, I should have made those a lot closer to the vacuum tubes. In fact, maybe even tried to mount the IF transformers actually on the circuit board, but boy, those do take up a lot of real estate. Well, I wound up putting 2-pin terminals in here, so one occupies this first socket hole, and then the third one, the middle one's not used, and then this one over here. So nicely, I have screw terminals for all the IF transformer in and out for the first stage and for the second stage. I also put a three position socket here for tuning, and I have one here for the RF coil. I did not use the antenna coil option that I created here, and also I added these switches for the phono switch and the phono plug-in, which runs back on a shielded cable from that point forward. Apparently somewhere in a radio circuit it's still picking up a lot of other things, and I guess I should have thought that out a bit more. Let's scoot this over, and yeah, there we go. So now we have our 12SQ7 here, and so also you notice the tube grounding and shielding is all connected together, and that seemed to work out. I probably went overboard with that, but it works. Now, also the volume control and the audio transformer are down here at the bottom with screw terminals as well. The screw terminal thing worked out really well for me. I kind of like things that way. I'm kind of used to working in that kind of electrical environment with screw terminals and things, and so this all turned out to be a good set with the design. Thought about making another one with the next generation, like 9-pin and 7-pin miniature tubes, well, I don't know. Think about that. I got a bunch of other things to do as well, so maybe sometime down the road. So now I'd like to share with you how I calculated the variable capacitors that I would need. You can't just go out and buy a dual ganged variable capacitor. It has to work for the AM band. There are certain parameters you have to follow. First thing, I have an IF frequency of 455 kilohertz that I want to use. That's what I bought my IF transformers for. That's what I'm using. I could probably tweak them up to 460, but anyway, point is, I chose 455, so I put this in here, and how this works is, yellow is all your inputs, so if you're prospecting a gained variable capacitor, you're going to put the min and max of the main tuning portion, that's the bigger one, and then the local oscillator, which is the smaller one, there's usually two of them and one smaller than the other, and as frequency goes up, capacitor size gets smaller. Then I'm going to have my band that I'm going to prospectively use, 535 1700 kilohertz, the AM radio band. And down here, it automatically adds the frequency of the AM band with the IF, giving a higher frequency. So we got 990 to 2155. Now, that takes the next column, the capacitance of the band, starting out at 355.2. Now, if you notice, it's taking the maximum and the trimmer, and then this one's taking the minimum and the trimmer. Alright, so then over here it's calculating in another area of the spreadsheet, it's calculating how many microhenries is needed to make this thing work. Now, if you were starting out and you had 0 in here in trimmer value, you'd see that this frequency and that frequency without a trimmer, it's got 106% variance. Meaning that I'm going to need a different coil to get this frequency than I will for that frequency. Well, that's no good. Well, so all I have to do is vary this number up here by trying different values. See, it gets smaller. 23. Smaller yet. 25. Wow, it's way down there. Let me back up to what I had originally. 25.2, there you go. And see, I could even take 25.25, that's too much. And you see, I could get crazy with this and tune it till it's very precise. But anyway, I can do that also with the local oscillator. Adjust the trimmer here mathematically until the lower frequency and the higher frequency use the same microhenry value, so that way the coil is fixed. Without a fixed coil, well, then you're going to need a radio that has a adjustable coil. You don't want to mess with that. We just want to adjust the capacitor. So now we have adjustable capacitance, fixed inductance, and it's a handy little spreadsheet for calculating this. But this allows you to see if your capacitor is going to work for you, or if you need to get something different. I'll have this where you can download this, and now that you see how easy it is to use, it's very useful. And now I want to talk about how I chose the output transformer. There's a bunch of these 70 volt and 25 volt system type transformers that you can buy from Parts Express and other places. And they've always been kind of a mystery on how to figure these things out. But there's some guys on the YouTube site had some really good information on how this is actually done. First, I want to show you that the secondary side is quite easy. common, and you have a choice of 4 ohms or 8 ohms. That's a no-brainer. So we just pick the common, and we pick our 8 ohm speaker, and we're in business. The primary side is a little more complicated. There is the common black wire on the other side, which there's the black on the secondary side, there's a black on the primary side. Don't get them mixed up. But how do you determine which one of these taps to use? Well, there is your tube, your final output tube. In my case, 12L6. There's the specs on the tube. And going down through the specs on the tube, I'm looking at various characteristics. The one I'm looking for specifically here is load resistance. Now, this gives me a load resistance for 110 volts system. It gives me a load resistance for a 200 volt system. I'm running around 180 volts, so I'm closer to the 4,000 ohms. So then, pop into the spreadsheet. I have 4,000 ohms. I wrote it down right here. Got those two numbers marked. I need something that has a load that works with a load resistance of 4,000 ohms. Well, on a 25 volt system, you square that number and get 625. On a 70 volt system, you square that number and get 4,900. So the way this works is he takes the squared number and divides by the wattage mark, and it gives you the equivalent load resistance, the resistance for the impedance for the transformer. 3920 right here at the 1.25 watts mark says that I got 3920. It's darn close to 4,000, and I wasn't quite at 4,000 anyway, because I'm running more, like I said, 170, 180 volts. So that's alright. Now, mind you, on 1.25 is my typical wattage of the system, pushing this little transformer a little bit hard, but it will work. And so now you know a good way to do this. So if you have a system with this load resistance, so you could get at 250 ohms here, you can get one at 1960 ohms here, you get different wattages for operation.